Good morning, Year 10s. How's it going, everybody? Has Ian disliked my video already? That is disgraceful. I am not entirely sure how I feel about that. Thanks, Ian. Feeding me. Oh, okay, you haven't disliked it. Okay. I'm just waiting for my YouTube video to pop up. No, Ian, you traitor. Feeding me. I know. I completely agree, Jack. Traitor. I'm going to pop out the chat. By the way, I've now given up on mute. I'm turning my camera off to give my laptop a bit more performance because I feel like that's a terrible thing to pause my face on. Okay, right. Let's crack on, folks. I want to try and be brisk. I'm going to share my screen. First thing we're going to do is going to do some. I know, by the way, for those people watching the YouTube video, I know that this is lesson 6 in the bonding sequence. The reason being is because I've been doing some lessons I've been doing on YouTube, some lessons I've been doing on Google Meets, and so I'm very aware that there's a gap in it, and I'm gonna try and fill those when I've got a bit of time. I will fill them so I've got the complete set. Yeah, I will do that. Okay. Oh, I'm gonna get rid of my face off the thing as well. Oh no, I've already done it. Amazing. Right. So straight in. Okay. So I'm going to put my little fan. I've discovered that if I keep my laptop a little bit cooler, then it seems to perform a little bit better. Okay, so we're on question 4, 5, and 6 of the word equation to symbol equations. So we're going to go through these, and then we'll do the last 4 in the next lesson, and then I'm going to set you another homework for you to have more challenging versions of these. So first thing we need to do, magnesium hydroxide and ammonium phosphate form magnesium phosphate and nitrogen trihydride and water. Wow, much more challenging. So, I'm going to shrink my pen down. So Mg, I'm going to make it, yeah, I'll keep it there. Magnesium hydroxide, words. So this is magnesium, I'm going to try and fit it in. Magnesium, it would have been better to have given myself some space. Magnesium hydroxide, have magnesium hydroxide plus ammonium. This is simply testing your ability to know where things go in terms of reactants and products. Ammonium phosphate, go to magnesium phosphate. So a phosphate ion has appeared at A level. It's quite nice. Nitrogen trihydride. Nitrogen. So habit for me to trihydride. If anybody's wondering why that one is a slightly different formula, it's because it's covalent, if anybody's interested, going to water. Okay, so now we need to convert that. So what I need to do is I just need to delete. I'm just going to go to white and go as far as I can and remove this, give myself a bit more space. There we go. I know that I'll make that reappear then when I go into the next question. So now we're going to translate this out. Translate this out. Right. So magnesium hydroxide. Ions. Okay. There are issues I'm having here, guys. Just want to show you this properly. So Mg2 plus OH minus, crossing down Mg brackets OH2 plus, right, ammonium phosphate, NH4 plus PO43 minus. I should really make my pen smaller. Yeah, NH4 plus. Crossing down. Yeah, I'm going to need 3 ammonium ions. That's a tricky one, that. If you can do that, you can do anything. Yeah, PO4. There we go. Going to magnesium phosphate. So this becomes Mg2 plus and PO43 minus. Crossing down. So Mg3, that's the 3 coming down, the charge obviously vanishes, brackets, PO4 brackets 2. Next, plus nitrogen trihydride. This is now covalent, hence why the name is slightly different. So this is just NH3. Oh, that's interesting, isn't it? Nitrogen trihydride. So that's the chemical name for ammonia. Isn't that in, there you go. And there it is, chemical name for ammonia. Next, plus H2O. Right, now we need to balance this equation. So we've got 1 magnesium. I'm going to shrink my pen down, balance in blue. 1 magnesium, 3 magnesiums. Okay. Next, I'm going to skip the oxygens and hydrogens because it's messy. I'm going to do the phosphates next. Yeah, I've got 2 phosphates here, only 1 phosphate here, so I'm going to balance that one. Put 2 in there. Right, now I'm going to do the nitrogens. This is a bit of a nightmare, isn't it? So I've got 3 inside there, but then a 2 as well, so 6 in total. So I'm going to put a 6 there. Then I'm going to do the hydrogens. Now, this is extremely messy. Extremely messy. So I've got 2 hydrogens there, but times a 3. So in total 6. Yeah. And then I've got 12 hydrogens. 3 times 4 is there, times by 2. 12, that's 24. So 30 in total. Now, this is the problem here. I've already got 6 times 3 there. So 6 times 3, 6 for 18. And I need to get to 30. And I've got 2 hydrogens in each one. Yeah, I'm going to say 6 times 6, so 18. So I need 12 more. Add a 6 there. Right. Now I need to do, now the phosphates are already done, so I can ignore those oxygens. Now what I need to do is, I now need to look at this from the other oxygen perspective. So I've got 2 there, times by 3 is 6, and I've got 6, it all adds up. Let's just do a quick check. This is a bit of a nightmare. Yeah, so ignore all of that. Oh, no. Okay, there we go. So, MG. Come on, put it back. Okay. So let's just check it. 3 magnesiums, 3 magnesiums. Oxygens, so I've got 2, 6. You can even do it this way as well. There's a 4 and a 2, so 6 plus 8. So that's 14 oxygens on that side. Put the bracket back in because I deleted it. So I've got 8 there. 8 plus 6 is 14. That adds up. I like it. And then, so that's the oxygens and then the hydrogens. Hydrogens is a messy one. Yeah, so 3, 6 there, but then 12 times 2, 24, so 30. 30, yeah, 30 all adds up. I like it. 30 adds up. And then the nitrogens, I've got 3 times by 2 is 6, and I've got 6 there, all adds up. Cool. That's a really hard equation, hence why I only want to do 3 at a time. So you guys can mark that with a tick if you got it correct. Can I have a quick show of hands on the classroom, please? On the chat, can you say if you got it or not? That would be amazing. I'm going to rewrite that out to be a bit clearer. In fact, I might put it on top of it. So the final answer is 3 mg brackets OH2 plus, can I just point out this is way too hard for GCSE. I will change that. Yep, so then it's just Mg3 brackets PO4 2 plus 6 ammonias plus 6 waters. Got it. Well done, Saru. Well done, Ian. Well done, Owen. Good job. Cool. Right, let's move on to the next one. I know I'm ruining all the notes. Doesn't really matter, does it? Right, so this one hopefully will be slightly easier. So we've got iron. I'm going to shrink my pen so I fit everything into the gap. Yeah, so I've got iron 3 bromide, plus ammonium. Again, we're just testing your understanding. Ammonium sulfide to form iron 3 sulfate. Sulfide, gotta be careful, plus ammonium, switching to, it's so hard for me not to do it, ammonium bromide. Okay, 1 mark. Right, change to symbol. Can I just point out, you get a mark, each one of these is worth 3. 1 for the word, 1 for all the formula being correct, and 1 for the balancing. Right, now I need to convert it to symbol. Okay, so Fe3 plus Br1 minus, FeBr3 plus, right, ammonium sulfide, NH4 plus plus S2 minus, cross and down, brackets NH4 brackets 2S going to iron 2 sulfide, iron 3 sulfide, sorry, S2 minus, cross and down, Fe2S3 plus ammonium bromide, ammonium and bromide, cross and down. Oh, that's nice. It's already done for us. Cool. So you get 1 mark for those formulae. Now we need to balance it. So 1 iron. Oh, too big. 1 iron, 2 irons. Okay, 2 irons now, 2 irons. I like it. Let's go BRs. Oh, now this is clever. So now I've got 3 BRs there, but times by 2, so 6. And I've only got 1 over here. So I'm going to multiply that by 6. There we go. So BR's now balanced. Next, blue, I'm going to treat the ammoniums as a single entity because it hasn't changed. So over here, I've got 6 of them. But over here, I've only got 2. So I'm going to multiply that by 3. There we go. This is much, much more GCSE. Still beyond GCSE, if I'm honest. 3 sulfides, it all adds up. 3rd mark if you got it. So each of these equations is worth 3 marks, guys. I've given you 10 questions on the worksheet, so it's going to be out of 30. Right, final one before we move on to my lesson. So we've got cobalt 2 sulfate, cobalt 2 sulfate reacts with lead 2 nitrate to form arrow, forming cobalt 2 nitrate. Yeah, so it's a switcheroni. Oh, sorry. Cobalt 2 nitrate and lead 2 sulfate. I like it. Right. Okay, convert to symbol. 1 mark for that, guys. 1 mark for that. So cobalt 2, it's telling us the charge. Sulfate, SO4 2 minus. Just got to learn your complex ions, guys. The charges cancel out. CO, SO4. Can I just make a quick point here, which is I often see students doing cobalt like that. You can't do that. That's carbon monoxide, yeah, or carbon dioxide. You got to be careful. Cobalt is a smaller O, so be careful of the capitals and lowercase. Just be careful. And then S, very common for them to do that as well. Please be careful. That's not the case. It's a capital O because that's sulfur and that's oxygen. So just be aware of it. Yeah, so there's cobalt 2 sulfate plus lead 2 nitrate. So that's Pb2 plus and NO3 1 minus. Cross and down. So I'm going to need Pb brackets, NO3 close brackets 2. Going to cobalt 2 nitrate. Okay, so cobalt is 2 plus, nitrate, NO3 minus, cross and down, brackets are needed, NO3, close brackets 2, plus lead, Pb2 plus SO4 2 minus, right, becomes PbSO4 because the charges cancel. I like it. Notice that in no final equations are any ions in there. Now we need to balance it. Yeah, 1 cobalt, 1 cobalt. Next. 1 sulfate, treat it as an entire entity. 1 sulfate, so far, so good. 1 lead, I'm going to switch to a different color. 1 lead, 1 lead. This is good. This is working. Yeah. And then 2 whoa, can't do that. 2 nitrates, it's all balanced. There we go, guys. It is already balanced. That there is what is called, it is a true displacement. That there, whoa, that's fat. That there is a true displacement. Yeah, they've just switched. True displacement. I like it. So guys, total marks out of 6. You can also add that to the 6 we did in the previous lesson, and we're slowly adding to our score sheet. Yeah, which is good. Right, today's lesson. Let's move on. Let's speed this up. So we're on to Ionic. We're on to bonding lesson 6, which is ionic properties. Last lesson, and I know we didn't do this one on YouTube. Last lesson, we achieved these 3 learning objectives. We talked about ionic compounds having this giant ionic lattice structure. And we looked at the pictures that we saw. We saw these diagrams. And then we looked at how we have to draw them for GCSE. There's the GCSE picture. You only actually have to do it with six ions in total. And there you go. There's the GCSE picture. And we talked about where the marks came from. Yeah, the fact that there's positive, negative, positive, negative, positive in this sequence. Yeah, and then the opposite on the other side. Yeah, we talked about that. There's one mark for them being alternating charges, but then the symbol and charge on the ion is the second. So that's the picture you draw for GCSE. And then we talked about what impact this structure has. Yeah, we talked about the ionic structure, this giant lattice. We talked about what the word lattice meant. It has a regular repeating pattern. Yeah, and then we looked at the diagram, and then we talked about this. We talked about the question of melting point. Yeah, and we talked about Susan Boyle singing Nellie the Elephant. Now, I know you guys probably don't know who Susan Boyle is. You can create your own acronym for it, but this is what we were talking about in terms of the structure. It was helping us reinforce this concept of what the structure is. So today's lesson, we're moving on, and we're looking at the properties of ionic compounds. Yeah, we're going to identify all the properties that you guys need to know. We're going to explain each property with a diagram, and then be able to identify objects in the house. And that's going to be your homework, to identify objects in the house which you would predict to be ionic. I like it. Okay, so first thing I'm going to get you to do, guys, is a task. Task number 1. I'm just going to shrink my pen down. Oh, no, I don't want to zoom in. I want to keep my writing fairly consistent. Let's go for that. Okay, task number 1. Task 1. Okay, so what I'd like you to do is draw a diagram of magnesium oxide lattice. Yeah, brackets, 6 particles. In the exam, by the way, it will actually say a minimum of 6 particles. Now, this is a reinforcement activity from the previous lesson. So, guys, what I'd like you to do is pause the video, have a go at drawing this in pencil. Draw it in pencil. Yeah, and then check to see if you get it right on the lesson. So answer. So we're now looking at this but previously we were looking at sodium, or we did lithium chloride before. Yeah, so now we're looking at this from magnesium oxide. So number 1 is we know it's going to be ionic immediately. Yeah, at GCSE, we see metal, which is magnesium, bonded to non-metal, yeah, which is oxygen, and we know that this is going to be ionic. So they're not going to tell you that in the question. You see, that's the first step in the process of bonding. Can they identify the type? Yeah. So now what they need to do is so since it's ionic, I know I'm going to have a repeating pattern. Got to be careful that they don't overlap. Yeah. And I need 6 particles. There you go. There's my 6 particles. And now it needs to go positive, negative, positive, negative, positive, negative, positive, negative. We need to have this repeating lattice pattern. And this is where the charge comes in. So Mg 2 plus, O 2 minus. Mg 2 plus, O 2 minus. Mg 2 plus, O 2 minus. And we're done. 2 marks at GCSE. Nice and easy. Yeah, nice and easy. We can also, this question of drawing the lattice, that's the lattice question. They can do the other question, of course, which is draw the ions within it. So I'm just going to do an evolution of this particular task. And in fact, I'll give it to you as task number 2. Yeah, so you can tell me how many marks you got. Do we have to write the charges? Yes, Masaru, you do. It's actually super important. Yes, because if you don't include the charges, then you're not showing it's ionic. You have to write the charges. It's really important. Yeah, you need the symbol and the charges. Okay, let's do task number 2. This is an evolution of this. And as I said, we've done this in lessons as well. It's quite nice to go back and have a look at this and where this appears. Have I done this? Yes, we did. We had these questions here from the exam showing the formation of ions. We did the reaction of them. That was in lesson 2. So it's nice just to give you a second question, task number 2. Yeah, draw a diagram. Diagrams in bonding are so important. Draw a diagram of the ions in magnesium oxide. Let's stick with the same thing. Yeah, let's stick with the same thing, magnesium oxide. It's a different question. Rather than the lattice structure, yeah, do we have to show magnesium particles as being smaller than the oxygens? Oh, wow, Zaina, that's awesome. No, they won't care, but I love that you know that. That I am super impressed with. You do not need to know ion sizes in comparison at GCSE. It's nice to know that the metal is always smaller, though. It depends on the ionic compound forming, really. But usually the negative ions are larger. Sorry, negative ions are smaller. Apologies. So the ions in this are going to be Mg square brackets, that says ion, 2+. Notice that I'm not showing any outer shells. This is because, this is a nota bene, yeah, no shells at all, due to Mg losing outermost. Yeah. If the question said show all electrons, then you have to do them. If that question was the case, then you'd add in these 2 shells here. Yeah, and you'd have them being 8 on the outs. There you go. That would be the full diagram if it asked you to show all electrons. But as I said, in this one, it didn't need to. The other one, of course, I have to show oxygen's outer energy level. And it looks like that, square brackets, 2-. This is called a dot and cross Lewis diagram. This is a Lewis dot and cross diagram. So if those words appear in the question, then you know exactly what you're drawing. But it's nice to do this. You only have to show 2 in that particular one because the lattice structure is designed for you to show multiples, but the ions in it, you only need to show 1 repeating unit, which is what that is. Okay, so let's move on to my learning objectives. So question number 1, what properties are there? Okay, so properties of ionic. Properties of ionic. I'm going to put compounds, but I always like to say objects as well. Properties of ionic compounds. So property number 1. Yeah, number 1. There is a crazy high melting point. Crazy high melting and boiling point. Melting and boiling point. Right, we need to explain this using a diagram. So the diagram, change my color, nice to do so. The diagram is the lattice structure. I'm just going to show, by the way, just to show you this picture here. This here is GCSE. GCSE. The A-level version, just for fun, yeah, just to show you the A-level version, looks like this. Mg 2+, O2 minus, O2 minus, Mg 2+. It becomes 3-dimensional. O2 minus, Mg 2+, O2 minus. There we go. So that's the GCSE, sorry, that's the A-level version of that image. We realize that these here, so that diagram, why does that diagram tell me a crazy high melting point? The reason being is structure, bonds, strength, number, energy. It doesn't actually tell me the strength one. Yeah, but it's nice to mention this. The structure, yeah, structure, giant ionic lattice. Giant ionic lattice. Yeah, bonds. The electrostatic attraction. Electrostatic attraction between oppositely charged ions. Between opposite charge ions, which is that there, yeah? And then strength. The diagram doesn't show this, yeah? So technically you'd skip it if they asked you to explain why the diagram shows this. Yeah, you'd skip it, but these bonds very strong. These attractions are very strong. This is the same process you run on any melting point question. This one is included. This is the number of bonds. Yeah, there are millions of bonds. There are millions of bonds. And that is shown by the diagram because there are bond. There are millions of them in this structure. It's endless. And therefore the energy to break, lots of energy needed to break. Lots of energy needed to break. And I'm just going to mention, you know, this here, this process, yeah. Susan Boyle sings Nelly the Elephant. You can come up with your own one if you like. Singers. The problem is you can't then, I don't want to add any more letters in. I don't know. Singers BTS sing Nelly the Elephant. You can do that if you like. I don't like the BTS bit though because it's I'm trying to make it, you know, Malaysia friendly. This here explains melting point. You always do this on every question, even at A level. You run the same process. Yeah, it doesn't change. Right. So they've got a crazy high melting point. Next property number 2. Property number 2. They conduct electricity when molten. Now molten literally means that there translates to hot liquid. We've melted it. Yeah, we've melted it. Molten means you've melted it. Yeah, if you want to translate that out as well. We have melted it. So it's become a liquid and hence molten. When molten or in solution. Right, now we need a diagram to explain this. Now, in electrical wires, I don't know how much you guys know about electricity yet from physics, but in electrical wires, you've got electrons in the wires that are free to move to carry the charge through the wire. Yeah, the charge carriers in metals are electrons. So we can make a little nota bene of that. Yet in metals, there are free moving electrons. Just to point out, when I teach you metals, we will talk about them being delocalized. I'll add that word to you now. Free delocalized. I'll add that now. Why not? Do it in blue. Delocalized. Free delocalized moving electrons that carry the charge. Through the structure. Carry charge through structure. Now, this is not the same for ionics. The reason being is ionics have no free electrons because the electrons are owned by the non-metal. Delocalized sea of electrons. Yes, that's correct, Signer. Yeah, so metals have free electrons, but ionic compounds don't. Yeah, so a nota bene here. Yeah, ionic compounds, I'll make it smaller. Ionic compounds have no free electrons. The electrons are owned by the non-metal. The non-metal has taken them. We know this from this diagram. The electrons which magnesium gave over are owned by the non-metal. Yeah, all the electrons are owned by somebody. But when you have, I'm going to do this with an, no, I ought to draw it first and then show you the animation. So if we've got, this is our solid sodium chloride. So I've got to be careful I don't overlap. Got to be really careful. So there's our solid sodium, our solid sodium chloride. Yeah, the ions are locked in position. They're vibrating, yeah, but they can't move. When we now make it molten, so we heat and melt, yeah, what does this now look like? It now looks like this. Yeah, it now looks like that, but the ions are now free to move. Now, why is this important? It's important because if they're free to move, they can carry the charge. The non-metal carries the charge. Just to show you this, electrolysis. This is them actually dissolved in water. Oh, I'll show you. Can I give you an ionic? Annoyingly, no, I can't. That's irritating. Let's go for, yeah, okay, let's just stick with that one. So in this situation, what you realize is the negatives, yeah, you can see that the negatives are all moving towards this side, towards the green side, yeah, where the green particles are, they're moving to the right-hand side. Let's do high. There we go. Click go. Right, so when electricity is running, the greens are moving to the right and all the blues are moving to the left. Now notice how the blues are all accumulating over on the left-hand side, and then when the negative gets to the other side, it drops off its electron and it moves around the circuit. So it's all because the ions, the negative ion is carrying that charge. And so the ions are free to move when molten or in solution. So that's a key thing there. Explain. I'm going to change my size. I'm getting slightly larger. I don't want to. I'm getting bigger and bigger in my text, aren't I? And I really don't want to. Okay. Question. Don't want to get larger. Question. Why do ionic compounds conduct electricity when molten? Notice I really need to hammer this. When molten or in solution. Yeah, they always ask, when do they conduct? So I'm just trying to really hammer that. Why do they? And the answer, you can pause the video and write down from listening to what I said earlier. So yeah, answer. I usually flip it the other way around, but my colors have ruined this for me. Let's go for green. Answer. The ions are free to move. 1 mark. To carry the charge. Through the structure. 2nd mark. So in the diagram wise, yeah, in a diagram, the diagram would look like this. So we've got the positive electrode, and I don't like circling it, and the negative, yeah. And what now happens is that when molten or in solution, it doesn't make any difference, yeah. This is the positive electrode. This is the negative electrode. It's nice to add those words. I'll change my color. Electrodes. Electrode. Yeah. And what now happens is the positive ions, let's make that bigger. The positive ions will move towards the negative. Yeah. And the negative ions will move towards the positive. Opposite charges attract. Now we know that the negative ion has an extra electron. Yeah, and the positive ion has lost its shell altogether. Now, when that ion strikes the surface, when the negative ion strikes the surface, it will drop off that electron. That extra electron, it will spit out. And the electron now runs through the process. It lights up my light bulb. Bling. Yeah, we see the conductivity. And then the electron then drops back down on this side and is collected by the positive one when that one strikes the plate. Yeah, when that strikes the electrode, the electron is then gained. Yeah, that's what's happening right there. It's kind of neat, that. So it's all to do with these ions being able to move. That there is so important. That there, put in a bubble. Yeah, because they ask this a lot at GCSE. Okay, so we've now got a diagram that explains that one. Next one is they are brittle. So property number 3. Property number 3 is they are brittle. So why are they so, what does the, first of all, what does the word brittle mean? So check this out. It's always nice to use the internet for, if I just type in brittle and hit images, boom. Yeah, this is what, oh, dearie me. Yeah, should have figured that would happen. By the way, it's brittle. Oh, let's go brittle property. Let's try that. Is it going to give me, there you go. Oh, just to show you something that's really cool, a video. Yeah, see if I can find a video of this. Video. Slow motion glass smash. Yeah, this is quite literally what brittle means. Oh, it's giving me a, let's mute that, it's giving me an advert. Skip, there we go. Right, all I want is the slow motion bit. Yeah, of the actual glass breaking. Come on. Give me the slow-mo. So that's what brittle is. Let's see the slow-mo of it. Isn't that one bit broke off first? Wow, that's brittle. Brittle means that if you are to bend it, it will shatter. Yeah, it'll break. Yeah, so let's now turn that into a diagram. Yeah, they're very brittle. So will shatter when bent. Yeah? Okay, so draw a diagram. Lattice. I'm just going to make it generic. Okay, easily done. There we go. So we know that there is an immensely powerful force between every single one of these ions. These little lines like this. Yeah, I want you to realize they're not solid bonds. It's an attraction. Yeah, these here are electrostatic attractions. Yeah, there are millions of them. Millions. They're very strong. Yeah, it's explaining why they're hard. Glass is hard, very hard. Yeah, but they're also brittle. If you do bend it in, hang on. So it's not elastic or stretching. That's right. Yeah, absolutely, Gayatri. It's the opposite, exact opposite of elastic and stretchy. Yeah, they are not ion. So anything that's elastic or stretchy is not ionic. Yeah, so these are very strong and there are millions of them. Now, if I hit this, yeah, if I were to hit this, let's hit it here. Yeah, this is where I ought to do like a 3-stage diagram. Yeah, I'm going to take my hammer. This is going to be a really bad diagram of a hammer. I'm going to take my hammer. There we go. Take my hammer. I'm going to take my hammer and I'm going to hit my ions. I'm going to hit my glass. Here's what happens. The ions get shifted. The ions have suddenly been shifted. You can see the original, what it looked like originally. Yeah, I've hit it and shoved it that way. Yeah, notice the original diagram. Notice the new diagram. Now, this is a big problem because what's going to happen is look what happens to the forces. Yeah, these, we now have like charges next to each other. Like charges. And what do like charges do? Repel. So what now happens in my diagram is that it will now become this. Draw the bottom layer again. They will then push apart. Yeah, the layers will simply repel each other. Yeah. And so it shatters. They all suddenly move apart. Yeah. And so you see a crack. So that there is explaining why when you hit something ionic, it shatters. Because they repel each other. You only have to move them over one ion. Just one. One single ion, and they will repel each other, and then the whole thing will shatter, and it'll be like a knock-on effect. It's like a domino rally. Yeah, just to show you that. Speed of glass breaking. Oh, that's really annoying. Come on. Speed of glass breaking. Go. Right. These guys here did an amazing thing. You can see I've watched this before. Yeah, see if I can make it full screen. So what they did was check this out. They took a pane of glass. Oh, I need to rewind it a bit. They took a pane of glass and they wanted to work out how fast glass can smash. So this is definitely worthwhile having a watch of, guys. It's really cool. Check this out. Look, he's got his hammer and he's going to hit the end of the glass. Whoa. He's not actually hitting it there. He's using a pair of pliers to bend and shatter it that way. But watch the slow-mo of it. Look how fast. Look at that knock-on. Imagine all of those ions all moving over by one single atom, and all of a sudden they repel each other and they split away. So you see the cracks forming. So you can actually see it's amazing that they actually calculate the speed of which glass smashes. It's amazing. It's a really cool video. I really love that. It's great value in it. It's amazing. Let's get rid of that. So 3 clear properties that we come across for ionic compounds. We can now come to my learning objectives and say, number 1, we've got the 3 key properties. High melting point, they conduct electricity when dissolved in water or when they're molten, when they're liquid. They don't conduct when solid, and they're incredibly brittle. So 3 clear properties. Then we said, can we explain each of those with a diagram? Yes, we can. You've now drawn all 3 diagrams. Now what I need you to do is identify objects in the house. Right, so would anybody like on the chat, please, to give me an object in the house that you believe is ionic? House, household ionics. Question mark? On the chat, please, whenever you're ready. In fact, what I'm actually going to do is I'm going to end this lesson here, and I'm going to see you guys over on the Google Meet. And, oh, actually, you know what? No. I'm not going to do that. I'm going to end it there. I'm going to set you that as a homework. And next lesson, we're going to fill out that. We're going to discuss. Well done, Ian. Ceramic is correct. Well done. Ceramic mugs. Yeah. Ceramics are actually a little bit more complicated, Ian. But yes, they are, in essence, ionic. Yes. Crazy high melting point. Very, very brittle. Trying to prove that they conduct electricity. Salt. Well done, Zina is correct. Yes, well done. So, guys, I'm going to leave you be there so you guys can have a think about that for your homework. And I want you to actually have a look around the house and maybe take some photographs with your phone of objects in the house where you go ionic, ionic, ionic. See if you can find some. That would be really entertaining. Right, I'm going to leave you guys there. Have a great rest of your day, Year 10, and I'll see you all soon. See you next lesson.